All right, we're back. We're on page 8 of Calc AB Notes 15. We're looking for a better way than actually writing a Riemann sum every time, taking the limit of the Riemann sum every time. So what I want to do is I want to return to the idea of like all of our Riemann sums that we've been taking the limit of have been right Riemann sums. But we know other types of sums, right? We could take a left Riemann sum, a midpoint Riemann sum. I'm going to actually switch over to GeoGebra to show you a kind of neat thing that it has built in. That like no human would really want to do by hand. But I mean, I guess you could. So I have a function here. It's defined in a weird way. So let me just show you quickly like how I defined it. So I'm going to use the point tool and just click like a couple of, I'm going to do 4 points, right? I, J, K, and L. And what I'm going to do is I'm going to say, make me a polynomial. And then it just give it a list of points, I, J. You can see it's now doing a polynomial through I and J, K, and L. So I just give it the list of points. So that's how I made this function that we're looking at, the kind of purpley one. I just gave it a list of points, but I didn't want to see all of it. So you can do another thing where you just say function. Okay, so function, what function? G, but I only want to see G between, let's say 2 and 6. I press enter. Now if I turn off G, you can see that I'm only seeing the part of G that happened between 2 and 6. And the neat thing is when you define it this way, if you move these points, it'll change the function for you. You can actually like really mess around with it by changing the order of the points. But so that's how I created this. And I think it's a really nifty way to do things. I do it a lot when I'm creating things specifically, you know, to demo things. So I'm going to delete all of these, maybe. I think as soon as I delete this, it's going to delete everything that depends on it. So G and H are going to be they're just going to disappear, and they did. And then this, I'll delete these. Okay, so this is my function. Now, the reason we're here is to see how this can work. So hold on, I'm going to mute and unmute myself just so I can see this thing bouncing. Okay, so yeah, I don't know why it does that now. It like stops showing me that the microphone is working, and it's like terrible. Okay, so rectangle sum is a thing. Rectangle sum, function, start value, end value, number of rectangles, position. Position is the most interesting thing. So rectangle sum, function, start, end. Let's do 8 because we're going from 0 to 8, so it'll make like 8 nice rectangles with like nice, the intervals will be nice, 0 to 1, 1 to 2, etc. So now I need the position. So this is going to be a number between 0 and 1. And what it tells you is like what percent of the way to go between the start and the end point. So if I say 0, it'll use the left endpoint. It's not going to, it's at the endpoint and it goes 0% across. So you can see, these are, hold on. I don't like this color. Click, okay. There you go. All right. That's a good color. All right, so we did 0. So it's always using the left endpoint because it goes 0% of the way across. If I make it 1, it'll go 100% of the way across, which means it's going to use the right endpoint. So you can see right endpoint, right endpoint, right end, etc. Now the idea is if I use enough rectangles, the error goes to 0 anyway, so it doesn't matter what type of rectangle I use. I could use midpoints. So I want to go 0.5, go halfway between them. And you can see now it's using the midpoint. So this is a very nice way of getting a good a graphical, a visual representation of these things. And also it does it so fast. What's weird-ish to me is that this will take any number. So we can go 75% of the way, right? So I'm gonna hit enter and it's gonna go, the easiest one to see is the first one, right? So from 0 to 1 goes 75% of the way, it puts you at 0.75. And you can see that's basically where the height is. And then it'll be 1.75. 2.75, 3.7, and so on. So it's always going 75% of the way across. We could go 0.1, right? So the first one will be at 0.1, then 1.1, 2.1, and so on. So 0.1. So we're doing this. Why would you do this? I don't really know, but it doesn't matter because if you do enough of them, the error goes to 0. Now, an amazing thing that a computer can do, that a human can do, but it'll take forever, is you can find something called an upper sum. So notice this doesn't ask you where you want the rectangle because what it's going to do is on each subinterval, it's going to find the highest possible function value and use that as the height. So upper sum f 0 to 8. And I need to tell it how many, but I don't need to tell it where to do it. So if you look, it's gone from 0 to 1, the highest is at the left endpoint. The right endpoint. From 1 to 2, the highest is at this relative max. Oh my God, say all the wrong words. At the relative maximum here. And then here it's at the left endpoint, switches to the right because that's the highest on this interval. The highest on this interval is the right endpoint. On this one, there's a relative maximum, so it uses that. And then the left endpoint. Crazy, right? It would take us forever. We'd have to do the candidates test on every subinterval and then choose the highest, and it just seems really prohibitively annoying. If you are wondering if there's a lower sum, there is, and it's the same deal. F, 0, 8, do 8 of them. So now it's always taking the smallest. So on the first one, I think there's a relative minimum where it's choosing, and then the right endpoint, the right endpoint. It's always the smallest. Here, I can't really tell. I think it might be the right endpoint, but it might also be this relative minimum. And then the same here, it might be the left, but it might be the minimum. And then left endpoint just misses there. And then the right endpoint. So it's always choosing the smallest function value. This is a crazy idea, but it makes sense. And it's not bad. Like if you want an absolute lower sum, an absolute upper sum, you have to do the candidates test on each subinterval and use the absolute max or the absolute min. Computer calculator just does it for us, so we don't need to worry about it. I'm gonna go back to the notes and develop this idea. So keep that in mind. Like we could choose left endpoint, right endpoint, midpoint, 0.7, like 75% across, 10% across, 25%, whatever. Choose anything. Use an infinite number. The error goes to 0 anyway, so we don't really care what we choose. So let's see what we can do here. So what I'm going to do is I'm going to make 2 assumptions to make life easier, maybe to sometimes make life easier. The first assumption is that the bounding function is actually the derivative of some other function. So what we're saying is that this function that we're going to integrate is actually f prime. So we're just making that claim. We're going to assume that that's true. It's not always true, but we're going to assume that it is and work off that and come to a conclusion. And then it'll be true every time we can make that assumption. And then the second assumption is that the bounding function, so this f prime, is continuous between the vertical lines. So f prime has to be, so first it has to be the derivative of something, and it has to be continuous between the bounds. So on this interval, this thing is continuous. We're making those 2 assumptions. Now, when we make those assumptions, we get a couple of pieces of information about the original function, right? Because we're saying that this is f prime that is now continuous on the interval. So if f prime is continuous on the interval, then what do we know about f of x? Well, we know 2 things. If f prime is continuous, then that definitely means f of x is differentiable, for sure, because f prime is continuous. And the fact that f is differentiable or f prime is continuous means that f is continuous. So f of x is also continuous. So we have f of x is differentiable and f of x is continuous. Well, what does that tell us? That tells us that we can definitely use the mean value theorem, since f of x is continuous on the closed interval AB and differentiable on the open interval AB. MVT applies. Where are you going? What? No, get out. Okay, hold on. Hold on, everybody. I don't know what's happening here, but I'm stuck. APP, I don't know. Oh yeah, APPLI. It was spelled up there, so that's good. So mean value theorem applies. Here's a weird idea though. The mean value theorem doesn't just apply on AB in this case. The mean value theorem actually applies to f of x, not necessarily to f prime. It applies to f of x on every subinterval. So if we go from like here to here, MVT applies. From here to here, MVT applies. Everywhere, every little subinterval, you can apply the mean value theorem. I'm gonna come back in the next video and I'm gonna kind of do that. So we know we're making big assumptions. Well, we know one thing. If we use an infinite number of rectangles, it doesn't matter what kind of rectangle we use. So that's the first idea. Then we're assuming that the bounding function is f prime. We're assuming the bounding function is continuous. Both of those mean the function is continuous and the function is differentiable. So we can use mean value theorem. So that's kind of a summary of where we are so far. I'll be back in the next video to do a little more, so I will see you there.